Okay, we are still considering this hyperboloid, x0 squared plus x1 squared plus xd squared equal to h minus second. And we're gonna now, we discussed the generic things about the geometry of this space, etc. Now we're gonna provide coordinates in this space. Well, for example, this hyperboloid is embedded into the space with the signature dx0 squared minus dx1 squared minus dx d squared. So one can solve this equation very easily, for example, by x0 equal to hyperbolic sine of ht divided by h, and xi equal to ni times hyperbolic cosine of ht divided by h, where I is running from 1 to d. So actually I is running over this, guys. And if ni squared, sum over i's is assumed, is equal to 1, so this defines a unit sphere, ni, we obtain that these two things solve this equation. Now if we plug this into here, from ni we obtain d minus 1 dimensional sphere. We will discuss it in a moment. So the metric that is induced on this space from this metric is equal to dt squared minus hyperbolic cosine squared of ht over h squared d omega d minus 1 squared. So this is a sphere, d minus 1 dimensional unit sphere, and it appears exactly from this guy. Exactly from this guy. And how to see that? Let me explain it. So for example, this equation, which defines d minus 1 dimensional sphere in d-dimensional space, can be solved as follows. We can define n1, which is cosine of theta 1, and theta 1 is ranging between minus p over 2 to p over 2. Then n2 equal to sine theta 1 times cosine theta 2, and theta 2 is ranging between minus p over 2, and so forth, up to n d minus 1, which is sine of theta 1, sine theta 2, sine theta d minus 2 times cosine of theta d minus 1, with theta d minus 1, all these angles ranging in this range, and at the same time theta d minus 1 is ranging between minus pi and pi. Remember that, well, let me finish first and then I'll explain what is going on. And d is equal to sine theta 1, sine theta 2, sine theta d minus 2, sine theta d minus 1. So the situation is very similar with the case of two-dimensional sphere. Remember, there are two angles, phi, which is ranging exactly in this range, and theta, which is ranging in this range. This is how we cover two-dimensional sphere only once, and that is exactly the same situation that we encounter here. So all the angles, except this one, take this range, and only one angle ranges here. In case if d equals to 2, d equals to 2, we obtain only one angle here, phi, or theta 1, which is ranging in this range, in fact. So that is a circle. So we're going to draw this in a moment again, but let me just say the following thing, that d omega d minus 1 squared, if we use this, which solves this, and plug it here, we obtain that this guy is just nothing but sum over j from 1 to d minus 1, and product of over I from 1 to j minus 1 of sines square of theta I times d theta j squared. This is a metric on unit d minus 1 dimensional sphere. Actually, by the way, Wick rotation can be seen already on this metric if we change ht to I theta d minus pi over 2. If we do such a change in this metric, then we map this metric to 1 over h squared times d omega. So this metric is mapped to this d omega d squared. So which is exactly the map between de Sitter space and d-dimensional sphere. And now one can straightforwardly see the meaning of this picture that I drew. So when we have h0, which is in fact simply changes homogeneously, raising from minus infinity to plus infinity. This is a x1, x2. We obtain this hyperboloid every time slice. Constant x0 corresponds to constant t. So every time slice of this hyperboloid is just a sphere, d minus 1 dimensional sphere. For this two-dimensional case is just a circle, because in this case we have a one-dimensional sphere, which is a circle. And actually using this, one can see that hyperbolic distance is expressed as follows. It's just minus hyperbolic sine of h t1 times hyperbolic sine of h t2 plus hyperbolic cosine of h t1 times hyperbolic cosine of h t2 times cosine of omega, where cosine of omega is nothing but n1 scalar product of f1 of and n2, where n1 and n2 are these vectors defining first and second point. So now the geometry of de Sitter space becomes apparent, and we're going to continue with the consideration of Penrose diagram to discuss causal properties of the de Sitter space. We're going to continue with the discussion of Penrose diagram for this space.